Okay, so we get to talk now about how the spectrum looks when you place a sample in the instrument and collect a spectrum. Now, the first thing that I need to mention is what's going on with the magnetic fields. Now, when you place your sample in the presence of external magnetic field, the sample is going to align itself with the magnetic field of your magnet. And they're both going to be going in the same direction. That's kind of what it means to be aligned. You have the overall same trajectory for your magnetic fields. And then the magnitude of your magnetic field from the proton, or the nucleus of your element, your target element, it's going to have a certain magnitude associated with it. So then you will have to input a certain amount of energy to basically excite it to the excited state. But that's that would be the story if you just had a proton, and really you would only see one signal which will be identical every single time. But here's where the electron comes in, and at first this may look like it's a problem, but this is in essence one of the reasons why we can tell what functional groups are going to be present in the molecule. So if you consider the following: the proton, which has a positive charge, and spin up, so it's in the lowest state, will have a magnetic field that's going to be pointing upwards in this diagram. Now the electron is also spinning up. It has a spin up, and um, what that creates is its own magnetic field. But then this is the little caveat, and this used to be something that even I kind of overlooked. Now the fact is that the charges do affect the position of the magnetic field. So if you have a spin up proton, then you have a magnetic field pointing upwards in this direction. But if you have a spin up electron, because the charge is opposite to that of the proton, the magnetic field actually points in the opposite direction. And it's all because of the charge. The charge affects the position of the magnetic field. So then, considering that and the fact that they both have to be spin up to be in their similar ground state level, if you will, what ends up happening is that the electron opposes the magnetic field, the external magnetic field, and so it kind of limits how far you're going to go. So you could look at it this way: you are kind of decreasing the amount of strength that the magnetic field has, and so instead of having to go just up until where the orange line goes, because the electron magnetic field is kind of like decreasing the power associated with the external magnetic field. Now you have to either increase the magnetic field, the external magnetic field, to match it up with the energy difference, or conversely, if you keep using the same magnetic field, you will have to use higher radio frequency energy to make up for basically this counteractive effect of the electrons. So you kind of end up decreasing this thing. So you could do that. You could increase the magnetic field and match up now excited state with the neutral state. Um, and make it so that you end up exactly at that transition where you turn the spin up proton into spin down, and you actually get energy to be absorbed, and ultimately that can lead to a spectrum. But this is one of the aspects that the electrons cannot affect, and you can think that, okay, the more electrons you have around your nucleus, the more energy you're going to have to put in just to get an actual absorption to happen. And so this is where the shifts in the NMR spectrum end up appearing. And this is what allows us to tell what's happening. Now, in order to fully understand this, what you need to also consider is the fact that there are different elements that you can have in a molecule. And each one of those elements has its own electronegativity associated with it. So from the point of view of the proton, which is going to be the element we're going to be focusing on quite a bit in this lecture. From the point of view of the proton, which has an electronegativity of 2.20, well, all the elements in red tend to be more electronegative. And of course, carbon is just a little bit more electronegative. But by the time you get to oxygen and the halogens, the electronegativity tends to be quite drastic. as far as the difference goes. So what ends up happening is that if you're observing or trying to get an NMR spectrum, you don't care about how many electrons oxygen, fluorine, sulfur, chlorine have, because you're not looking at the spectrum of oxygen or fluorine. You're looking at the spectrum of hydrogen. And so if you bind hydrogen to any of these elements that are more electronegative, what these elements will do for you is remove electron density away from the hydrogen and allow you to excite the protons of that hydrogen with a lesser amount of energy. Now, on the other hand, if you use elements that are less electronegative, like boron, silicon, or metals, well, then your electron will have a lot more energy density, excuse me, a lot more electron density. And what this would mean is that you will have to absorb a much higher energies just to have that absorption taking place in the first place. All right, now let's say that you're actually looking at a carbon spectrum. So you're trying to collect information about carbon. Well, the story is actually kind of similar. Nitrogen, oxygen, the halogens, and even sulfur are more electronegative. So you will see electron density taken away from carbon and allowing you to use less energy to resonate your carbon isotope. But if you have hydrogen bound to carbon, you have phosphorus, silicon, boron, well, those elements are less electronegative than carbon, so they will actually increase the amount of electron density around it and make it a little bit harder to to get it to resonate. And by harder, I mean you're gonna have to put in more energy. So if you actually make a plot of where the peaks of absorption show up as a function of the magnetic field that you're using, well, you have peaks that show up at lower energies, closer to the axis. And so these are the peaks that we will call electron poor. And the farther out on the right side of this diagram that you go, well, that's when you encounter situations where you have a lot of electron density around the nucleus that you're observing. So we call them electron rich. And of course, the in between will be the intermediate kind of region. Now, in order to get to the electron poor case, you want to have electronegative or highly electronegative elements bound, if not on your proton itself, nearby. Okay, so nitrogen, oxygen, sulfur, halogens nearby to the proton you are observing are going to create an electron poor situation. And then if those elements are a little bit farther away from the proton that you are observing, well, then you'll start having intermediate effects. You won't be like all the way down on the spectrum. You might be somewhere in the middle. And then if all you have is just carbon and hydrogens, well, that's going to be the situation where your electronegativity difference um, is not very different. You're going to have a lot of electron density on your element, so you end up showing up a higher magnetic fields. This will be your electron rich situation. And if you end up using silicon is even less electronegative than hydrogen. So this will end up pumping a lot more electron density on the element that you may be trying to observe. So what ends up happening is that if you read in your textbooks is that tetramethyl silane that contains silicon is often used as a reference, because being less electronegative than carbon and hydrogen means that both carbon and hydrogen are going to be with the most electron density around them, and they will require the most energy to be resonated. So these peaks tend to fall really high up in the spectrum. And so we use that as a reference. And oftentimes we just call it TMS for to abbreviate it. So tetramethyl, tetramethyl silane, TMS. All right, now because the electron poor signals fall very close to the having no magnetic field, we call this the downfield region, because it requires lesser amount of magnetic field. But the regions that are electron rich, that fall farther to the right on the spectrum, we call them the upfield, because they require less magnetic field to make it resonate. So if you look at an example like the one right here, this is a simple example uh, where we're looking at 2-methyl propane with, well, technically 2, which is 1,1,2 trichloro 2-methyl propane. All right, so that's the molecule. What you will see is that if you're looking at protons specifically, well, you have this proton in blue, and then you have the protons in the methyl groups, which are equivalent to each other, and those are the only hydrogens present in this molecule. So you only see 2 signals. You see 1 signal for every kind of hydrogen that your molecule possesses. And notice that the blue hydrogen is bound to a carbon that has more chlorines, more electronegative atoms around it, whereas these protons right here are, connected to a carbon that only contains one chlorine, and also they're farther away from the chlorine, right? So what you would expect is that the peaks of the methyl groups over there are going to fall higher upfield on the spectrum compared to the blue hydrogen, because this one is less electron rich as a result of having more chlorines nearby. So this one shows up farther downfield on the spectrum. And I'm gonna refer to the spectrum in a second as to why you see these numbers, because you might have noticed the numbers are looking kind of funky. You have a higher value on the left side of the spectrum and a lower value on the right side. That's because this spectrum is not shown in terms of the magnetic field strength, but rather is shown in terms of something we call ppm. I'm going to talk about it in just a second, but let me show you another example again. So here I just have dichloro, 1,1 dichloropropane. So the blue hydrogen, once again, which is closest to the electronegative groups, it shows up farther down, excuse me, up, yeah, up downfield, excuse me, downfield, right? Because we're closer to the intersection of the x and the y-axis. So this shows up farther downfield, and then the CH2 and the CH3s. Well, the CH2 is closer to the chlorines than the CH3, so what you see is that the CH2 appears, in the intermediate region, and then your CH3, which is the farthest away, appears um, the farthest upfield in the spectrum. Later on, we're going to talk about as to why the shape of the peaks are the way they are in the spectrum, but for now, you just want to concentrate on the positions. So notice that this carbon, the one that is farthest away from the bromines, is going to be showing up the farthest upfield on the spectrum, so the one closest to the right side. Then the CH2 is going to be somewhere in the middle. And then you kind of have a situation that's a little bit ambiguous, because you have this pink hydrogen, which is bound to a carbon that contains a carbon-bromine bond, but so is the situation for the blue hydrogens, right? Those hydrogens are also bound to a carbon with a bromine. So you might ask, well, which one is meant to fall downfield, which one is meant to fall upfield? And the way to tell is by looking at the oxidation state. So notice that from the point of view of carbon, the oxidation states are going to be determined by the electronegativity differences, right? Because hydrogen is less electronegative than carbon, so it will donate electron density to carbon. But bromine is more electronegative than carbon, so it will withdraw electron density away from carbon. So if you look at the carbon over here, this carbon is bound to 3 hydrogens. The 3 hydrogens donate electron density to carbon, and we can just take it to the extreme and say that, okay, for each hydrogen, or better yet, for each bond to the carbon, we're going to donate electron density to the carbon. There's 3 hydrogens, so this will give you an overall -3 charge oxidation state for the carbon. The carbon over here is bound to 2 carbons and 2 hydrogens, so you end up yielding a -2 oxidation state for the carbon over here, right? And notice that we have a 0 right there, because carbon bound to carbon, there is no difference in electronegativity between those two elements. So we just say 0 for that, and -1 for the hydrogens. Now the blue hydrogen over here is bound to carbon, 2 hydrogens, and a bromine. The bromine withdraws electron density, so it gives you +1 charge. The hydrogens add electron density to the carbon, so they give you -1 each. And altogether, this is a -1 oxidation state for that carbon. The pink carbon, on the other hand, is bound to 2 carbons, 1 hydrogen, and 1 bromine. You get a +1 for the bromine, -1 for the hydrogen, 0 for the carbons. So the oxidation state of the pink hydrogen is 0. And so now what we can do is look at the oxidation states to figure out what's going to happen. And looking at that and that alone, you can say, well, since each one of those hydrogens is on a carbon that contains a bromine, um, the oxidation state now will tell you what's going to happen. And notice that the carbon that is the most oxidized is going to be the one most willing to withdraw more electron density away from hydrogen. So we're going to assume that the hydrogen bound to the carbon that's most oxidized is indeed going to be showing up farther downfield, right? And in this case, it's not a huge change really, because they're very close to each other, but they fall a little bit farther downfield. And you can kind of tell by the magnitude. This peak is smaller in quantity because it only corresponds to one hydrogen. This peak is larger in quantity or height because it corresponds to twice as much hydrogen. Okay, the last thing I'll mention before we end this video is how we come up with these plots, and what's the deal with those with the x-axis. Why do we have that inverse numerical sequence? Well, that has to do ultimately with the idea that you could look at how much magnetic field it will take you to promote the absorption of turning the upspin to the downspin proton. But alternatively, you could say, well, we could keep the magnetic field constant, and instead of changing the magnetic field, we could change the frequency that we are providing to the sample. And this is now how instruments, do NMR in general. We keep the magnetic field constant and we vary the frequency that we are supplying to the instrument. And this is your typical NMR instrument that you would see in most research laboratories. So what ends up happening is that instead of looking at the picture from the point of view of the magnetic field, we're now looking at it from the point of view of frequency. And typically what we do is we have to use a reference. So that tetramethylsilane molecule, that's the reference molecule. And so we look at the frequency at which it absorbs. And then we compare it to the frequency of absorption of our sample, and we take the difference. We divide that by the frequency of the instrument, because you could have different instruments. Some of them are 200 megahertz, 100 megahertz, 400 megahertz. So this is a means of kind of like bringing everything to the same overall playing field. And then we multiply by the ppm unit, which is a million. So what you end up seeing is that the magnetic fields here are megahertz. So this is 400 megahertz. You could have 200 megahertz, etc. And mega stands for 10 to the 6. So the 10 to the 6's cancel out, and this is the main reason why we use ppm for the scaling of the spectrum, simply so that we cancel out the exponents. And so what you end up doing, if you want to calculate this, is just take the frequency difference of your reference from your sample divided by the megahertz value of your magnetic field, and then you get the actual peaks. And because you're kind of taking the difference of this, now what happens is that um, the values down here are kind of inverse, as to what you were expecting. Instead of having 0 all the way to the left, you have it now all the way to the right, because now this is from the point of view of the reference, and the reference appears all the way upfield in the spectrum. So that's what reverses the value of this spectrum overall. So don't get confused by that. Downfield is still you being closer to the left side of the spectrum. The ppm values happen to be higher on the left side, and then the right side is still the upfield situation. You're farthest away from the crossover between the x and the y axis, but the ppms are pretty much 0. And in some samples, you could even go to negative values, but we won't touch upon that factoid in this class. Okay, in the next video, I'm going to talk to you about the common shifts that you observe based on the functional groups. And after that, we'll start talking about the constants that you expect to see for different functional groups. So see you in the next video.